beginning part F of section 3.2. We're going to move on in some more definitions here. The rates of change. We talk about velocity in this class a lot, and velocity is our instantaneous rate of change. We talk about it as instantaneous velocity because it is the derivative. Let's get down here. S is s of t, the position function we just talked about. Moving along a straight line, the velocity of an object t is v of t, and it's defined then as the difference in the outputs of the position function divided by the difference in the inputs. Again, what we've done here is build our limit definition of the position function. Now again, we're going to just recognize that velocity is the derivative of the position function. So if we're looking at the velocity of something and we already know the position function, we take its derivative, we have now found what the velocity is. Okay, so how do speed and velocity compare? It's a good question. In many people's minds, they're the same thing. However, speed is the absolute value of velocity. If I say that something is traveling 60 miles per hour, that's all I know. 60 miles per hour. I don't know what direction. It could be going east or west, north or south, or some other direction. I just know that it has speed of that. Velocity is going to have a direction applied to it. If we are looking at the position function of a free-falling object, we are looking at s of t equals 1/2 g t squared plus v sub 0 t plus s sub 0. Now we've looked at that just briefly earlier on, and I know you've looked at it in Algebra 2 books, probably in physics class. If we're looking at the initial height of the object, so I'm going to drop this object from a 10-foot height, then s sub 0 is going to be what we use for that. I'm going to give it a little bit of thrust, velocity at the beginning, so v sub 0 is the initial velocity, and then the acceleration due to gravity is then g. We're going to be given that value, and so and we're going to be talking about on Earth. G is approximately equal to negative 32 feet per second squared. If we go into the metric, it's approximately negative 9.8 meters per second squared. So we're going to need that information. So our position functions won't have a g in it. It'll have either a negative 32 or a negative 9.8 on there. Okay, here's an example. A ball is thrown straight down from the top of a 500-foot building, initial velocity of negative 48 feet per second. What is the velocity after 3 seconds? So let's answer that question first. Again, velocity is the derivative of position function. So I need to build a position function. So if I look for a position function, and I know that it is 1/2 g. Now we're talking about on Earth here, and so we're going to put in negative 32 for the gravitational pull. Gt squared plus it has an initial velocity, so it's negative 48t, and we are throwing it down from a 500-foot building. So that's going to be our position function, and we need that first before we can continue on. So let's look at what would be our derivative. Actually, before we do that, let's just do one more thing with this, and let's just write this as negative 16t squared minus 48t plus 500. Okay, now if we look at the derivative, we'd have negative 16 times 2, take the exponent times the leading coefficient, and subtract 1, minus 48t, so 48 times 1, and then subtract 1 from the exponent, plus 500, and let's look at this. This could actually be t to the 0 power. T to the 0 is 1. And so if I do this, I'd have the same rule. I take the leading coefficient times the exponent, and I subtract 1. Now, the rest of this is really not necessary, because if I'm multiplying by 0, that's going to go away. Go back to the first set of notes on this section, and we might be reminded that if we have a derivative of a constant function, it is equal to 0. So we're going to have here negative 32t minus 48. That's going to be our velocity function. Now it says after 3 seconds. So we have here that t is equal to 3. So we're going to actually look at the derivative at 3 seconds, remembering that that's the same as the velocity at 3 seconds. So negative 32 times 3 minus 48. And if you do those calculations, you come up with negative 144 feet per second. Okay. So what's the velocity? This ball is traveling negative 144 feet per second as we're dropping, as it is dropping down. And the negative tells me that it is falling. Now, what is the velocity after falling 100 feet? We have to think about this. After falling 100 feet, the question is, what is the position after falling 100 feet? So the position now is 400. So S is going to equal 400, which is going to then be equivalent to negative 16t squared minus 48t plus 500. Why is that important? Well, let's think about it. Velocity, it says what is velocity? So now we have to ask the question, what is the input in the velocity function? And the input is time. Are we given time? No. We're given 100 feet. What can we gain with this? Well, if we know that it's already fallen 100 feet, the question becomes, how long did it take for the ball to drop 100 feet? Okay, so if we know that the position now, and again the position's above Earth, is now at 400, we have S equals, actually let's go back. Let's go back and let's realize again, think about this again. We've got 400 equals negative 16t squared minus 48t plus 500. If I subtract 400 from both sides, I get 0. Negative 16t squared minus 48t plus 100. Okay. I need to do this, think about it, in order to solve for t. This is now a quadratic function, and so if we use the quadratic formula, and I can only use that when I have the quadratic set equal to 0, x equals plus or minus let's see, x equals the opposite of b plus or minus the square root of b squared minus 4ac, all of it divided by 2a. So I can say that t equals the opposite of negative 48 plus or minus the square root of negative 48 squared minus 4 times negative 16 times 100. All of that divided by 2 times negative 16. Okay, again, something you did back in Algebra 2, if not maybe sometime in Algebra 1. If you do all the calculations correctly, you would have that t is equal to negative 3 plus or minus the square root of 34 divided by 2, which is approximately, now let's talk about this plus or minus. If I get a negative in here, that's going to mean that time has a negative numerator divided by a positive denominator. Time is negative. I don't think they've perfected yet going back in time, so we'll just pick up the positive of that and have it come out to be 1.42 seconds. Now, this is an approximate, and when we use this in our next calculation, we're going to want to use the exact, and so the exact would be negative 3 plus the square root of 34 divided by 2. So keep that in mind. Okay, let's go back. What is the problem asking? It says, what's the velocity after falling 100 feet? So the first question we had to answer is, how long did it take for the ball to drop 100 feet? It took approximately 1.42 seconds, or exactly this amount of seconds here. If I want to know velocity, then I need to know the velocity of negative 3 plus the square root of 34 divided by 2. Velocity, again, is the derivative of position, so it means we have to put it back into this, negative 32t minus 48. So negative 32 times this quantity and minus 48. If we look at that value, our answer is going to be approximately negative 93.295 feet per second. Now, could we do this on the Inspire? Absolutely. I would recommend that you find the derivative of the position function and then use that, use this value into the velocity there.